This narrated PowerPoint presentation is entitled A Historical Reconstruction of the Major Land Uses in the Oldman River Watershed of Southwestern Alberta. The work was prepared for the Oldman Watershed Council and completed by the ALCES Group in 2012. First of all, let's position the watershed. It's found in southwestern Alberta. It's 23,000 square kilometers, and we can see here the major cities and settlements of Pincher Creek, Claresholm, Fort Macleod, Cardston, Lethbridge, Coaldale, and Tabor. So that is the study area that we will be discussing in this presentation. It's a phenomenally diverse landscape, gradient from west to east of reducing elevation, the alpine, subalpine, montane communities and foothills to the west, to the east, the native grassland communities, which today have been largely replaced by agricultural complexes, and in between the foothills. Now the combinations of slope, aspect, relief, elevation, soil types, and climate, which have created these phenomenally distinctive physiognomies, have also created an equally diverse set of plant communities which support a phenomenal diversity of both flora and fauna. Looking down in plan view on the study area, one can see again the alpine, subalpine communities to the west and the foothill complexes. Here we see the Porcupine Hills and the major settlements. In slanted view, or transverse view, we can see what the landscape looks like if we're viewing it from the west, looking from essentially the BC border out to the east. And these kind of perspectives help remind us of the texture of these landscapes. Here we're looking from the north, looking south towards the United States, and again, the mountains of the western part of the basin there, the headwaters. Here we're looking east towards west, and very clearly one can see the fabric of agricultural complexes that have shaped the eastern component of the basin. And here we're looking south from the United States, looking north into Canada, and again seeing the heterogeneity of landscape types and certainly the pattern of land use footprints. So what we're going to do here is look at the suite of overlapping land use practices that have shaped this landscape. Here's the base layer showing topography, and again the major plant community types, the alpine and subalpine, the foothill complexes, and then out into the native grassland communities. So the phenomenal gradient in elevation and structure of plant communities. Here, and flashing in orange, is that proportion of the grassland communities and foothills that have been converted into cultivated land. Flashing now are the settlements, from the large ones like Lethbridge to the much smaller communities. Rural residential, these are farmers and ranchers, but most of them would be acreage complexes today. The major and minor roads and some additional GIS footprint called truck trails. The rail system, transmission lines, the well sites and where they're found and dominated, the pipeline network delivering hydrocarbons to market, lagoons associated with communities and other industrial complexes where water treatment is required, a variety of industrial features flashing here, primarily associated with the hydrocarbon sector, gravel pits, the dugouts, and last are the borrow pits. So collectively, these are a suite of overlapping land use practices that have been shaping this community. Now, in terms of count, there's about 27,000 of these polygonal footprints, and this does not include any of the agricultural conversions. And of those, the most common ones are rural residential and well sites, about 10,000, about 4,000 dugouts, about 1,600 various small industrial features primarily associated with the hydrocarbon sector, then down into 206 for gravel pits, and smaller numbers for settlements, lagoons, borrow pits, etc. So that's count. In terms of area, there's about 103,000 hectares of these footprints, again, not including croplands, and the most common in area, or expansive in area, would be that of pipelines, 37,000 hectares, minor roads, 21,000, settlements, 13,000, and then on in decreasing area. With respect to edge, or the border of these land use footprints, there's about 50,000 kilometers, and the most common are that of pipelines and minor roads. I should say that the seismic line data is not included in this particular data set, and then followed by well sites, rural residential, major roads, railway, dugouts, power lines. So showing the distribution of land use footprints and expressing them in edge, in area, and in count. Now, this landscape is much busier today than it would have been 200 years ago. Most of the surface water has been allocated to a suite of land uses. This basin is fully allocated. Work done in the basin by the provincial government has indicated that water quality has certainly changed and that there's an elevational gradient from good to fair and in some cases even poor. So reminding ourselves that there is a signature here, a signal that as we have grown the intensity and expansiveness of land use in the basin, we're seeing some measured changes in ecological goods and services. So the project objective is to describe in both tables and maps the changes that have occurred in the Oldman River watershed during the past century, between 1910 and 2010, kind of looking at it decade by decade. This represents the first phase of this project, which is to take the landscape, help people understand how it's changed decade by decade over the last 100 years, what it looks like today, and how those changes have occurred throughout those decades. And then to provide an opportunity in the second phase to grow this landscape into the future for essentially 2 generations or 50 years, and to examine what would happen if the current suite of policies that are currently on the landscape unfold. Where would this landscape go, and what would be the benefits and liabilities, and then to contrast that perhaps with an alternative management objective as defined by the Oldman Watershed Council, giving them the opportunity to say, okay, we now understand how we've changed, we understand where we are today, what combinations of land use and space and time will optimize land use in terms of providing as many benefits as possible while minimizing environmental liability. So that the work that's being reported here could possibly extend into phase 2. Let's very briefly describe the methodology as used in this study. Now, first, a key caveat. Reconstructing the past 100 years of land use development is certainly an imperfect science. Available data for the Oldman Basin is incomplete in both space and time. We're using extrapolations and generalizations in the ALCES and ALCES mapper model to approximate the arrival of various land use footprints based on existing time-stamped data. And it provides us with a good strategic overview, a very plausible one, as to how these land uses unfolded through time. However, it would be inappropriate to use these products for tactical purposes or discussions about any individual landowner. It's not intended for that purpose, and it doesn't have that kind of level of resolution. In terms of building the arrival of these land use footprints, we used a variety of public domain data, and here we get to see them for the major and minor roads, railroads, seismic lines, pipelines and well sites, industrial sites, mines, gravel pits, transmission lines, settlements, rural residential, and recreation. Many of these data sets were current up until 2007, and some, such as seismic lines, dated back to 1995. Now, there's a suite of overlapping land use practices in the basin, and those that we were able to look at because of availability of data included mining, transportation, the energy sector, croplands, livestock, the human population, their settlement patterns, various assorted industries, and provincial parks. In the case of forestry, it is an important land use practice in portions of this basin, but we did not have access to cut block data, so we could not reconstruct that. And the footprints of First Nations, tourism and hunting, fishing, and trapping, those footprint data were not available, so they were not included in this study. So we needed a study area, that is the Oldman River Watershed of southwestern Alberta. We took that data, we stratified it into the various landscape types, we drove it into the ALCES model, and then we used a variety of algorithms and logic rules to reconstruct it over the last 100 years. And in this particular phase, that being phase 1, we didn't have to worry about natural disturbance regimes or future land uses, so those portions were ignored. We went directly from essentially the historical land use trajectory to produce a series of products, which is graphs and tables and maps that are changing through time. And it's primarily maps that are the key output of this study. Now, the spatial scale that was examined is that of 5 by 5 kilometers. Initially, we talked about townships, and if we use townships as shown here, which is 10 by 10 kilometers, or 36 sections, you end up generalizing. So, for example, here we get to see the river moving through the northern part of this township, and if we were presenting our data at the township scale, its distribution would be generalized in this particular grid. But by moving to quarter townships, as shown here, 5 by 5 kilometer grids, the model would indicate that there were main stem rivers in these two northern quarter townships, but there wouldn't be any in the south. And similarly, the southern ones, which are more dominated by cultivation and even by irrigation, those practices wouldn't be extended into the north. So we thought that a 5 by 5 kilometer grid would be the most appropriate kind of sweet spot between generalizing and providing a level of resolution that is providing more detail. So if the grid is too big, then these land uses are generalized and spread over a much larger area than it actually occurs. And if the grid is too small, it actually suggests a level of accuracy that doesn't exist based on the data. So also displaying land use footprints at very small areas, high resolution, can unfortunately direct stakeholder discussion to tactical and personal levels or ownership, and that erodes the objective of the study, which is to talk about the larger, more strategic issues. So based on that, a decision was made with the Oldman Watershed Council to present the information at grid scales of 5 by 5 kilometers. In terms of temporal scale, the goal was to produce information decade by decade and then maps that showed how various indicators and footprints responded through time, as shown here. Some historical data sets are collected each and every year, and examples would be the hydrocarbon wells, water wells. When you know of a feature and you know where it is, you actually know what year it was constructed. However, many other footprints are collected maybe every 5 years, such as many that are collected by Statistics Canada, and some others are actually in very irregular intervals, and the road network would be an example there. So the historical footprint data and the reconstructive algorithms in ALCES map were used to estimate each cell's footprint at decadal intervals back to 1910. Historical data were available for a subset of footprint types, requiring the use of surrogates to approximate historical trajectories for other footprints. So here we can see those footprints where we had known arrival or construction dates or years, and we had to use those to serve as proxies to reconstruct others. So for example, when rural residential house built on the landscape, you can get that information by actually knowing the year in which the groundwater well was drilled. Similarly, by knowing the arrival of hydrocarbon wells, it's possible to estimate the time at which seismic lines and pipelines were built on the landscape. A variety of other features were used to determine minor roads and highways, and collectively then you're able to build a compelling story as to how each of these footprints arrived. So let's place the Oldman Watershed into the provincial context. Although the focus is the Oldman Watershed, it's helpful and I think constructive to understand how does its footprint compared to the province in which it's found. So here we see Alberta. These lines, of course, represent the distinction between the green, primarily public lands, and the white area, primarily private lands. And here we're looking at the reason we have land use, and that is we have a human population. And in black down here, we see the Oldman River Watershed. So as time marches on, human population increases. This is 1910, 20s, 30s, 40s. So we'll just march through right through to essentially today, the exponential increase of the human population, about 3.7 million people in Alberta, the vast majority in the Edmonton-Calgary corridor, and the highest densities start basically at the northern extent of the Oldman Watershed. Certainly there is a population there and you get to see its general distribution. We'll be providing higher input maps later as we zoom into the Oldman Watershed, but clearly the Oldman Watershed does not support the majority of Albertans that live in the province. Here we're looking at rural residential, so not everyone, but just those people that are living outside of settlements. And again, at the provincial scale, we can see how that has grown exponentially. So we're looking at the estimated number of residences up around, what, 250,000 rural residences in Alberta, and the distribution inside of the Oldman Watershed Council. Here we're looking at the transportation network. 1910, what would have been not too many decades before, were essentially well-established trails begin to become roads. The north-south Highway 2 and the east-west Highway 16, and then subsequently the Trans-Canada. So 1910, 1920s, and by 1930s, you can see the major highways have also already become conspicuous, but throughout much of the white area, the 2 by 1 mile public transportation network is now apparent. and it just grows through time as road density increases and it gets filled in. And in red, the higher density of roads is associated primarily with the establishment of higher densities of farmers as the farm size in many cases becomes smaller close to cities, but primarily the significant increase in rural residential in the Edmonton-Calgary corridor. Now in terms of croplands, 1910, there were many of these quarter townships that had some level of croplands. So the color here is yellow, indicating that a certain percentage, so light yellow here, between 10 and 30% of these particular townships are occupied by some croplands. And of course, as time marches on, the colors get brighter and deeper. For the case of the provincial map, these are townships. Over 85% of them are croplands. So we see that there's a significant amount of croplands in the Oldman Watershed Basin, and that the highest areas are on the northeastern component of the basin. Livestock populations are important in Alberta, and here we're talking about cattle. As we see from the graph, the provincial population has increased, although there's some decade by decade variation depending on disease and market drivers. And it's also very apparent that the cattle population is a very important feature of the Oldman Watershed Council. Here we're looking at the hydrocarbon wells and their exponential growth in the province of Alberta to about 300,000. And the Oldman Watershed Basin certainly has hydrocarbon wells again in the eastern third, particularly on the northern eastern third, but nowhere the kind of densities that we see in many other places in Alberta, such as north of Medicine Hat or north of the Oldman Basin itself, or in Sagdi Alley between Fort McMurray, working way down to Coal Lake and Lloydminster. So here, using data from the Alberta Biomonitoring Institute, this is very recent 2010 data. We're looking at the large mines in Alberta, that being bitumen, coal, and peat, and you can see them in blue. I'll just flash them off and on here, and we note that these footprints are not even found in the Oldman Basin. If we then move on to borrow pits, which are shown here in yellow, there are some. These are basically small surface excavations where material is removed from one area to be used for another purpose. It can only be 100 meters down the road from wherever the excavation occurred. There's some 18,000 of these borrow pits in the province of Alberta, and some, but relatively few, in the Oldman Basin. Here we're looking at dugouts in red, and of course the dots can only be made so small, so there's spatial exaggeration, but nicely shows the distribution. And not surprisingly, the dugout distribution in the province of Alberta is associated with the white area, it's associated with livestock, and since we've got a healthy and significant livestock population in the Oldman Watershed, there are equally lots of dugouts. Here we're looking at gravel pits, showing in green, and following, for the most part, the large riverine valleys. And yes, there's a significant population in the Oldman Watershed. In Alberta itself, there's about 2,300 of these pits. In terms of lagoons that are built to help process water from either settlements or other large industrial features, you can see the distribution in Alberta. There's about 750 of them, consuming a total of about 5,100 hectares, and some in the Oldman. Here we're looking at all of these small excavations, large mines, which you said are not in the basin, followed by lagoons, by gravel pits, by borrow pits, and by dugouts. So small surface excavations are important features in Alberta, and we get to see the distribution of them province-wide and in context to the Oldman Basin. So if we look at all of these footprints together, everything that's anthropogenic, but for a moment we're going to push croplands aside and to see their distribution. Here's 1910, and the total anthropogenic or human-caused footprint in the province of Alberta begins to grow exponentially, and you get to see the hot spots in Alberta where most of this is, again, associated with the energy sector, associated with forestry, energy sector here, the Edmonton-Calgary corridor, and of course the biggest footprint of all, which is cultivation, isn't even shown in this map. So the reciprocal of that is the fractional landscape that's natural, and of course it's declined, and if you look at the entire province of Alberta, it's been declining exponentially. We have lost at least 25% of all the natural landscape in the province of Alberta, and showing that there's a fair bit of natural landscape on the eastern portions of the Oldman Basin, but as you move east and particularly northeast, there's a gradient towards a greater percentage of anthropogenic features, therefore a gradient of reduction in natural landscape. And here we're looking at edge density, which is such an important indicator of so many ecological processes, and showing that edge density in the Oldman watershed is relatively low compared to many other areas in the province of Alberta. Now, if we begin to add all those land uses together, we can create what are called combined land use intensity metrics. And here we can see, in terms of the response of ecological goods and services to those, the reduction through time, and where overall land use intensity is considered to have had the greatest level of potential adverse effect on a broad suite of ecological goods and services, which could be water quality, water quantity, carbon in soils, and even biodiversity. Specifically looking at carbon in soils and in vegetation, here is 1910, again, before we have any land use or any significant land use, and of course there's not much carbon in the tops of mountains or in the Precambrian shield. You see that the foothill complexes are very rich in carbon, but our native prairies are also holding a significant quantity of carbon in their natural form. But as decades unfold, we see two major vectors occur of gradual incremental loss of carbon. And note that this graph doesn't scale from high to zero, but 305 to 290. So we're seeing a very slow but gradual loss of carbon in many parts of Alberta, but in recent years or decades, that trend has been reduced in certain areas through the adoption of direct seeding. So two major factors here to the north, that of incremental loss of carbon associated with additive logging and fire, in the south through many decades of intensive agriculture. In terms of water demand, if you're keeping track of all the people and all the livestock and all of the different forms of agriculture and industry, one can also quite nicely estimate the total gross and net water demand. And so here we're seeing water demand grow in the province of Alberta and growing exponentially as these land uses expand in diversity and scale and intensity, and see the hotspots in Alberta with respect to water demand. And the Oldman watershed represents a portion of Alberta that has a significant appetite for water, due primarily to cultivation and more specifically to irrigation. So water demand is an important feature of southern Alberta and specifically the Oldman Basin. Now, if we look at water quality, and it's indexed to 1 meaning that it's got the natural level of nitrogen, phosphorus, and water that we'd expect in a variation year to year without land use practices, and water quality as we move down from 1 towards 0, but it's scaled here between 1 and 0.75. As it drops, that reflects a proportional increase in the loading potential of nitrogen, phosphorus, and sediment. So a reduction in water quality reflects an increase in loadings, and the Oldman watershed, particularly the eastern two-thirds of it, is characterized by land use that has the capacity to significantly increase the amount of nitrogen, phosphorus, and sediment into water and making water more eutrophic. So if we look at all of these land use factors in terms of its effect on ecological goods and services, we get the following map. Ecological goods and services in the province of Alberta has been incrementally dropping. And again, this isn't scaled to 0, but to 0.75. And you can see that we've lost somewhere around 15 to 20% of the overall ecological goods and services based on the metrics we're looking for this study, which is water quality, water quantity, and carbon in the province of Alberta, and shows those locations where the effects are greatest. And the Oldman watershed is a very intensively used basin, particularly in the eastern two-thirds. So let's zoom in and look at the basin itself at a finer scale. These quarter townships are 5 by 5 kilometer grid scales. We'll start with the human population. And you can see as we move from cooler colors to hotter colors, the density of humans increases in a non-normal sense. We're using a special program that uses what are called natural breaks to maximize the amount of spatial noise or ability of people to see the differences in human density. So 1910, 20s, so the graphs on the right no longer refer to Alberta, but to the Oldman watershed basin itself. So upwards of what, about 180,000 people, and we'll just back it down here to 1910, 20s, 30s. In the 40s, again, the majority of people, the vast majority, would not be living in settlements and towns. They would have been living on the landscape, primarily in agriculture. But as time marches on, we see a shift from a distribution in the east. Okay, here's back in 1930. You can see the majority of people living in this proportion of the basin, but watch what happens decade by decade as we march on, and now we have higher densities of people living in the west. Now they've moved primarily into the towns and the cities and the acreage complexes associated with those. And here we'll just drape on the various settlements, and we see a very beautiful spatial concordance between the reconstruction in ALCES mapper and where these communities are today. So everywhere the community is, the settlements, you have high density. Areas outside these communities are either agricultural farms or ranch houses, or in many cases, acreages. Now, if we look only at rural residences, starting in 1900, moving forward, 20s, 1930s, again, here if we pause, look at the distribution of these rural residences, almost entirely all agriculture and found primarily to the east. But let's march forward and watch the east to west migration, showing that almost all of the rural residential is now found in the western half of the Oldman Basin, tied primarily to rural residential and acreage complexes. So about 12,000 of these residences on the landscape. And here we're actually draping over the dots that represent each of these houses, whether they be a farmhouse, a ranch house, or an acreage house. And you can see the beautiful concordance between where they're found and the grids showing their density. Cropland intensity, starting in 1910, here's 1920, so there's some level of agriculture spread throughout much of the eastern two-thirds of the study area, and as time marches on, the colors get deeper and brighter, representing a greater fraction of those townships are now being cultivated. And here we get to see the overall fraction of the total watershed that is being cultivated, and those areas that have the highest level of cultivation. Some areas very low, obviously the mountains none, the foothills sparse in terms of cultivation. They may have many livestock, but not that much cultivation. Porcupine Hills, but those areas that are heavily and intensively cultivated. In terms of the cattle population, as we see in the graph, decade to decade variation, but essentially increasing. We have about 9/10 of a million head of cattle on this landscape right now, and you get to see their distribution. So we'll just back up and grow it through time again. So decade to decade variation, but some significant growth in the current distribution. And of course, many of these cattle are being finished in feedlots, and so those quarter townships that have feedlots will have much higher density. Now, all land uses require a transportation system to move our goods and services throughout the landscape, and here we see the arrival and growth of the transportation network in the basin. And the major highway complexes are very easy to see. And we'll actually now drape over the main highways, secondary highways, and the minor roads. And you can see a beautiful concordance between where they're found and the density grid map. In terms of the hydrocarbon well footprint, whether it be natural gas or conventional oil or any of the hydrocarbon wells, we're not distinguishing between them in this particular map. 1910, 20s, first of all, we'll focus on the graph to the right and see the exponential increase in the number of producing hydrocarbon wells. And we'll back up and now focus on the map, showing that there's some significant densities along the very western extreme of the basin, but also to the east. And then there's some concentration areas here in the 1970s, significant wells in the very eastern edge of the basin, and that density increases through time. And it's primarily the eastern portion and the northern portion that have the bulk of the hydrocarbon wells that are producing in the basin today. And about 9,000 of those wells, and here we get to see their distribution. Now, some recently available data from the Alberta Biomonitoring Institute in terms of small surface excavations provided us the very first insight as to the amount and distribution of these small surface excavations. So let's start by looking at lagoons, and here you get to see as the orange dots where they're found In the basin itself, it suggests there's 38 lagoons occupying a total of about 140 hectares, and there you get to see their distribution. And just by looking at Google imagery, it's possible to zoom in and see some of these features. So that's what they actually look like when you zoom in. What about gravel pits? About 206 gravel pits consuming about 2,200 hectares. And you can see that the majority of them are aligned with the mainstream rivers in the study area. Some are not. Others are following these tributaries quite nicely. In terms of dugouts that are required or helpful to provide water to livestock, there's about 4,200 in the basin, consuming about 832 hectares, and here you get to see their distribution. So significant numbers. So if you look at the total surface excavations, there's our study area, 11 borrow pits, 38 lagoons, 206 gravel pits, about 4,200 dugouts, and that is the distribution of small surface excavations in the study area. Now we can also plot that as a grid map, and we do not have the history of these, but we do know where they are today. And here we see the distribution of these small surface excavations, some areas having much higher than others. So clearly a pattern through here, another pattern through here, and of course the western extent of the study area has very low densities of small surface excavations. So if you plot all of those, that is the distribution you see today of the small surface excavations. So if we look at all anthropogenic footprints together, start in 1910, again, not including croplands, you can see some of the hot spots, people basically homesteading in areas where they thought had good soils, good climate, and access to water. As we march forward, we see an exponential increase in a fraction of these watersheds that are characterized by land use. And here we see the final map showing the overall intensity of land use in the basin, but does not include that of croplands, and then draping all these footprints over top. Some areas receiving very significant pressure, others relatively untouched. In terms of edge, again, it's grown exponentially through time, and the grids go from very low densities, essentially no anthropogenic edge, maybe 0 kilometers per square kilometer in some of these areas here. And in red would be between 3.4 and over 8 kilometers per square kilometer. And some areas very intensively used on these slopes. And then let's drape over those linear features. So clearly the overlapping land uses are clear. Here's a variety of different natural landscapes, the mixed grasses, the dry mixed grasses, foothills fescue, foothills parkland, montane, subalpine, alpine, and the various hydrological features. And we can begin to look at how they've changed through time again as we lay out our cultivated land and many of the other footprints as they begin to flash on the landscape and indicate how busy it has become. If we take all the information presented earlier, it becomes possible to generate a generalized time sequence showing the various land use practices in the study area. So clearly there was a time where the dominant land use in the Oldman River Watershed would have been that of First Nations. They were the only people in the landscape, they were land use, they were making the decisions as to what happened where, and clearly they are no longer a dominant driving force, particularly with respect to participation in traditional lifestyles. There's still many First Nation people on the landscape, but for the most part they have been incorporated into Western economies. Following their dominance, starting in basically the early 1800s and peaking probably about 1830 and dying out about 1870, was a land use where almost all non-Aboriginal and many Aboriginal people were involved in, and that was bison hunting. And that was replaced by trapping. There was a time where, again, almost all European people and First Nations were involved in the land use called trapping. Forestry and mining arrives and has been occurring for a couple hundred years, but has never been a dominant or overwhelming land use on this landscape. Croplands come in the late 1800s and become the dominant land use and continue to be very important today, but maybe from a political standpoint are not as dominant as they were in the 40s and 50s. The hydrocarbon sector starts up in the 1930s and has become a very important land use practice, but maybe the most important land use practice we have today is that of just residential. The cities, the towns, the acreage complexes, that is a land use. and is occupying more and more of the landscape and has significant political leverage behind it. So in a very generalized way, and many people might disagree with this time series, but this is kind of my take on the transition of land uses through time in the last couple hundred years in this basin. But at about that point was the Palliser expedition. So interesting, as a harbinger of things to come, in the summer of 1859, the Palliser expedition was exploring southwest Alberta on horseback, somewhere probably in or very close to the Oldman watershed. And James Hector says to Peter Erasmus, who was a Métis hunter and guide in the Palliser expedition, "You must prepare yourself and your associates to adjust to a new order in this country. The progress of civilization renders this inevitable." Adds Captain John Palliser to the conversation, "Your work with our expedition is but a phase of things to come. All the great territory now sparsely populated by a few wandering tribes will someday be the homes of thousands of prosperous people engaged in agricultural pursuits, stock raising, and other industries that always follow the settlement of vacant lands." And those were quotes that came out of a book entitled Buffalo Days and Nights, published in 1999 by the Glenbow Institute. So it's interesting. We certainly talk a lot about cumulative effects of overlapping land use practices. Well, maybe they weren't using the same words, but Erasmus and Hector and Palliser could see it coming well before it did. So if we put all these land uses together, we get to see some of the other aspects that emerge. Certainly this land use needs more water, and here we get to see the significant increase in water demand, which is basically leveled off in the last few decades, but where is that water being used? And here we get to see the distribution. If you keep track of all your cows, all your cultivated land, irrigated or not, the people, the processing of hydrocarbons, any land use that requires water, here we get to see the patterns of distribution. So the units or number of cubic meters being used per hectare in each of these quarter townships. If we look at contaminant loading or potential contaminant loading in terms of nitrogen, phosphorus, and sediment, we get to see that water quality is declining through time because of increased loading. And here we get to see the map that indicates how that has changed through time in those portions of the basin that are primarily receiving greater levels of loading of nitrogen, phosphorus, and sediment. In terms of soil carbon, very slight and gradual loss of carbon through time from about 155 metric ton per hectare down to about 130 metric ton per hectare. That may not seem like a lot to some people, but if you look at the total number of hectares and the total number of tons, that carbon has all, of course, been released into the atmosphere. And the loss of it through time, and we'll just back up here, is primarily through various cultivation practices that incrementally have reduced the carbon in soils. Now, in the last couple decades, one could argue that instead of it continuing down, we've actually reversed it and are beginning to put some of that carbon back into the soil through direct seeding and other soil conservation practices. Some very encouraging news there. If you argue that there's a relationship between biodiversity of indigenous native species and the overall intensity of land use, and if you make generalizations such that many of our native species do not do well in monocultures of agriculture or live on highways or inside of industrial plants, then you can begin to map the changes or the estimated changes in biodiversity on this landscape. And some areas, of course, have not been touched at all, others in a very, very modest sense, but there's some hot spots. Areas that have a lot of people, a lot of agriculture, a lot of livestock, cultivated crops, some of them irrigated, and the footprint of the hydrocarbon sector and transportation networks, where this basin, if we measured biodiversity through space and time, such as the Alberta Biomonitoring Institute, should be exhibiting losses of biodiversity. The total amount of the landscape that's natural has been declining through time, and here we get to see those areas where almost all of the natural plant communities have been removed. The good news is that much of the western one-third still contains a significant amount of natural landscape. If we look at the total amount of land use intensity, so not only cultivated crops, but agriculture, livestock, forestry, energy sector, transportation, and human populations, we get to see the distribution of intensity. Again, the hot spots in terms of land use intensity is essentially the northern part and the eastern part. So the northeastern part of the landscape is receiving the greatest collective intensity of land use. Now, if you look at ecological goods and services on this basin, as measured by three, and there's many others that could be looked at. We only looked at three: water quality, water quantity, and carbon. Here we see the changes in ecological goods and services relative to the baseline of 1 in the last century. So some areas continuing to provide significant ecological goods and services to the landscape and to the people who reside there, and other areas providing many other commodities, but at an expense. And the trade-off there is ecological goods and services. So we'll leave it there. Hopefully this information will serve as a segue to a discussion on where the landscape is today, how it got to this point over the last 100 years, and hopefully this information will lead to other questions about the scale and magnitude of land uses that will drive this landscape into the future for the next 100 years, and finding those combinations of land use and space and time that maximize benefits while minimizing liabilities.